So a lot of people puking in my house right now. So yes, now my wife's not feeling good, so I need to go home, unfortunately. So we'll see how this goes. All right. I'd much rather be here with you people. They're going to be all thrown up and everything else. Yeah, Cody had it on Friday night. Then Sean got it yesterday. Now my wife today. So I'm doing my best to avoid it. So we'll see what happens. Yeah, so anyway, just a reminder about our K and Q stuff, right? Remember, with our KSP stuff, right, if it points towards the reactant side, right, that's the solid form, right? That's where the precipitate is at, okay? So keep this stuff in mind. Always put K in front of Q, all right? And if the reaction is shifting to the product side, that means that's the soluble side. If it's shifting to the reactant side, well, that's the solid side. That's where the precipitate is, okay? So pretty much they're going to give us some information here, and we're going to have to do a little manipulation in terms of moles of ions in solution and dividing by a new volume, because concentration of ions in solution is what's going to be important for us here. Okay, so if we look at this first example here, so we got a solutions prepared by adding 715 milliliters, 4 times 10 to the minus 3 molar cesium nitrate to 300 milliliters of 2 times 10 to the minus 2 molar potassium iodate, right? Will cesium iodate that has that KSP precipitate for the solution? Okay, well, the deal is, right, we're looking at this reaction here. IO3 solid, right, going to cesium ions, right, and 3 iodate ions, right? Because our KSP is equal to 1.9 times 10 to the minus 10, which is equal to concentration of cesium ions times the concentration of iodate ions cubed. Right. So what we need to figure out is we need to find the concentrations of ions that we have in solution. Okay? Right, so we need to know these. So we have a new volume of solution. Okay, we need to know those values, but we have a new volume of solution. So that means we need to, use the information we have to figure out how many moles of ions we have and then divide by the new volume. Okay, so we need to use the information they're giving us here. So for example, to figure out the concentration of our cesium ions in solution, right, I go up to the problem there, and I'm ultimately going to need to know, I need to use this info right here, right, for moles of cesium, or for concentration of cesium in solution, right, we've got 0.750 liters, and we have a solution that is 4 times 10 to the minus 3 moles of cesium nitrate per 1 liter, right? Okay, and I'm going to do this see, right? For every 1 mole of cesium nitrate that is dissolved in solution, there is 1 mole of cesium plus, right, floating around in solution. Okay, so that means then we have 0.75 times 4 times 3. So that means we have 0.003 moles of cesium ions in solution. Okay. And what's our new volume here? Yeah, our new volume here is 1,050 milliliters, right? 750 plus another 300 milliliters, we get 1,050 milliliters, which is divide that by 0.1050 liters, right? We determine the concentration is going to be 0.15. We've got 0.0286 molar cesium ions. Oh, yeah, it should be 1.05, right? 0.02. How did I do that? Yeah, sorry about that. 1.05, there we go. So that changes 0.003 divided by, so that's 0.0028, sorry. There we go, 1.05 liters. So that gives us 0.0028 molar for our concentration of that ion in solution. And then to figure out our new concentration of our iodate ion, right, we use the information that's given to us about that particular ion. And because we have to figure out what the deal is here, we've got 0.3 liters of a solution that is 2 times 10 to the minus 2 molar KiO3 per 1 liter. Well, the nice part here is, well, it's just 1 mole of iodate ions for every 1 mole of KiO3. So 0.3 times 2. So that ends up giving us 0.006 moles of iodate ions. We divide by our new volume, 1.050 liters. And we end up with 0.0057 1 molar iodate ions. Okay, so now we can calculate Q. Now we're ready to figure out where we're at here. Okay, so we calculate Q. Q is equal to concentration of cesium ions times concentration of iodate ions cubed. All right, so we've got 0.00286 times 0.00571 cubed. Times 0.0286. Wind up with 5.34 times 10 to the minus 10. So K, right, is less than Q, right? K is less than Q, so that means the reaction shifts towards reactants. Right? Reaction's shifting to the left, and this is the key component here, right? What's our reactant? The solid. It's a solid, so that's going to precipitate out a solution. Okay? So that's why we get a precipitate. Reaction shifts towards reactants, which are solid, right? Which equals PPT, right? So that's a yes. We're going to get precipitates. We're going to get that. This using my date, we have enough of the ions in solution that are going to combine together to form a precipitate then. Okay, so it's that simple. Find the ions concentration in solution, all right? Calculate a Q value for them, and then compare. If it points towards the reactant, you get a precipitate. If it points towards products, still have the ions dissolved in solution. There's not enough in there yet to precipitate it out. Okay, the concentrations are not high enough yet to make that happen. Okay. All right. So there we go. So on the next page here, we kind of broke it down a little bit. Okay, for you, but now there's kind of an extra thing that makes this. These are the toughest problems here, because now the next part is, okay, calculate the new concentration for the ions, right? That's what we did, right? We compared our Q and our K value, all right, to determine whether or not we're going to get precipitate. But now what they can do is, all right, we're going to precipitate to form, okay? And what they're going to want us to do is find the leftover concentration of ions floating around in solution. All right, so that's going to give us a little extra work. So we got to do some limiting reactant stuff, but the nice part is we'll have moles of ions, so we'll be able to do some addition and subtraction there, and it won't be too difficult. But it just makes for a longer problem, and it's the toughest problem that we have in the entire unit. Okay, the other ones at this point have all been fairly straightforward. Okay, not too difficult, but this one is a little more difficult. Okay, so there's a couple extra steps here. All right, so like in this problem here, they give us a solution. We're going to pour these two solutions together. They want us to calculate the concentrations of magnesium and fluoride at equilibrium. Okay, and that sort of thing. So, yeah. So they're actually telling us, hey, we're going to get a precipitate to form here, really, and then we got to calculate the different concentrations at equilibrium. Okay, so we'll walk you through this one here, and this is as hard as it can get, but it's not too terrible. All right. Oh, just like in our last problem, right? We've got our formula of magnesium fluoride, our KSP reaction here to fluorides, right? Our KSP is equal to 6.4 times 10 to the minus 9, right? And that's equal to the concentration of magnesium 2 plus times concentration of fluoride squared. Okay, so first thing, you have to find concentrations of magnesium, right? And fluoride flowing around. Okay, so our concentration of magnesium here is going to be equal to, we got to use this data here, right? So we've got 0.150 liters. Multiply that by 1 times 10 to the minus 2 molar magnesium nitrate per 1 liter. Right, that's a 1-to-1 mole ratio. So I'm going to write that out just to be complete. It's not always that way. So it's 1 mole magnesium ions for every 1 mole of magnesium nitrate. So we end up with 0.0015 moles of magnesium plus. Okay, what's our new volume for this? 50 plus 250, what is that? 400 milliliters, right? So we divide this by 400 liters. So we've got 0.00375 molar Mg2 plus. Okay, why don't you guys find the fluoride ion concentration? So if you've done that, go ahead and find Q now. That's the second thing we got to do. Okay, so when I calculated Q, I got 1.46 times 10 to the minus 5. All right, and that's a lot less than K. K is a lot less than Q. Yep. Oh, I don't know why I did that. Oh, I'm just missing a number here. I forgot to write in the 6. 0.0. 625. There we go. Oh, I don't know what I'm doing there. Thanks. I'm sorry. It does ultimately, right? You divide them both by the same, right? 0.03750.06253. Right. All right. There we go. Sorry about that. So ultimately, all right, hey, we do get a precipitated forms for sure. It's a whole, Q is a whole lot, or K is a whole lot less than Q, right? So the reaction is shifting to the left, okay? So what we need to do now, so the third part, and this is where the directions up there are telling you run the reaction to completion, okay? So we're gonna run precipitate reaction to completion, okay? Because we got to find the excess reactant. All right. We're going to find out how many ions are still floating around in solution. We're going to find out how many ions are still floating around in solution here. Okay. So we can kind of see, like, if we look at, pretty easy to see here, right? If I have 0.0015 moles of magnesium, right, and my mole ratio is 2:1, right, how many moles of fluoride would ultimately react with it to form or precipitate? Twice as much, right? Okay, so we can just set that up. You can kind of see like which one's eliminating reactant already, right? Right. So if we take 0.0015 moles of magnesium, we just use our mole ratio. Mole of fluoride will react for every 1 mole of magnesium. Make 0.003 moles of F minus. This is how much would react, right? Or how much we're going to use. Right? Well, we started with 0.025 moles of fluoride ions, right? Minus the 0.003 moles used. That's how much we started with, right? That's how much we're using. So we have 0.022 moles of excess fluoride ions, right? Kind of run out of space here. All right, so that's how much we got floating around. And now the final part here is, and this is kind of the tricky part, just keep in mind, just because we form or precipitate doesn't mean that none of it is dissolved, right? Real small fraction of it is actually dissolved in solution. Okay, and so that's what we need to ultimately find out, right? So we can just do an ice table like we have been doing with the common ion effect to do that. All right, so the fourth part here, the fourth step here is, and I'll kind of write this out just to make sure that we're kind of complete on this. Although we assume all the magnesium 2 plus goes into the plate, a tiny amount is still actually dissolved. It's still actually dissolved in solution. Okay, so just to kind of give me some space, well, I'll squeeze it in here. So MgF2, right, solid. So we're going to run a little ice table here with what we have left over, minus. We're going to assume we have 0 there. But now the key is, if we have 0.022 moles of fluoride floating around in a 0.400 liter solution, right? We know we have 0.055 molar fluoride ions floating around in solution. So that's how much fluoride is still floating around in solution. So we're going to plug that in as our initial and do our little ice table here. And we'll ignore the change like we have been. So KSP is equal to X times 0.055 squared. Sorry, this is taking up so much space. 6.4 times 10 to the minus 9 is equal to X times 0 squared. 0.00325. So X is ultimately equal to 2.12 times 10 to the minus 6 molar. That's equal to the concentration of magnesium 2 plus. Kind of a monster one. That's the tough one. All right. Okay, so that's a little bit of a tough one. That's as hard as it can get. It'll take a little while. So, yeah. All right. Rough one. All right, now you only have to do that type of problem when they ask you for the concentration of the ions of the solid at equilibrium. Okay, most of the time they never go that far, and they're always just asking for, is this going to precipitate or not? And then that's that. Okay, I very rarely do see a problem like this, but they're out there, so we work through one for you. Okay, all right. More of what you're going to see is stuff like this. Okay, is we just got to figure out which one's going to precipitate first. Yeah. I mean, there's potential for that. But that just took us, what, like 20 minutes? Just saying. Probably be different problems on free response, right? Yeah. But seen it on an AP free response before, though, so that's where it's there come from. All right. This is more or less what is really a problem that you're going to get and one that's going to be more useful here. Okay? So, all right. The deal is here, we have the solution. It's got copper ions, it's got lead ions. And we're going to add iodide to it, right? So we're going to add it gradually. The PbI2's got a KSP of 1.4 times 10 to the minus 8. And the copper iodide has a KSP of 5.3 times 10 to the minus 12. And they want to know which is going to precipitate out first. Which one are we going to start separating from the solution first? Well, the problem with that is that can we just compare KSP values there? We can't, right? We can't do that. All right, because why can we not just like look right at the KSP value? Yeah. Right. Each one of these has different number of ions in solution. So if that's the case, then we need to solve for X to decide which one's going to precipitate out first. Okay. So first thing they want to know is they want to know which one's going to precipitate out first, and then specify the concentration of iodide necessary to begin precipitation of each salt. Okay, so all right, we have enough information here for each of these that we need to do, do, do a couple ice tables here and figure out and solve for x, really. Okay, when we do this. Okay, so they know in our solution we've got, I'm going to write these up just to be kind of complete. You don't necessarily have to do this each time, but I'm going to write out the KSP formula just to make sure that for the KSP reaction. So we've got each of those written out there. Plus and minus. Okay, so for each one of these, we need to solve for, we know that we have 10 to the minus 3 molar of that guy. We know we have 1 times 10 to the minus 4 molar of copper iodide, right? So what we want to do is we got to figure out what the concentration of iodide is in each of these solutions that's going to precipitate it out, okay? So we know K P for this guy is equal to 1.4 times 10 to the minus 8, which is equal to concentration of lead plus concentration of iodide squared. So 1.4 times 10 to the minus 8 is equal to 10 to the minus 3 squared. This is equal to so we got 0.0026 what? 0.0026 molar I minus. Okay, so what we can see there is when you solve for x, once the concentration hits 0.0026 molar for I minus, the lead will start precipitating out. Okay, but once the concentration hits 5.3 times 10 to the minus 8 molar, right, that's pretty small, the copper will precipitate out, right? So the copper is going to precipitate out first before the lead does, right? Because as you're adding, the concentration of the iodine continues to increase, but once it hits that mark, then the copper iodide will start coming out first. Yes?
For the lead iodide, why wouldn't it be twice, like, in parentheses squared instead of just x squared?
Good question. Did I do that right? Oh, because there's no change. You just need to know what the concentration of the iodide will be in solution at that moment. Okay, so we just have to solve for that particular value. We're not looking at, yeah, that's right. Okay. Let's say here, just to be a little more complete, copper iodide will precipitate out first because the concentration iodide is much lower at 5.3 times 10 to the minus 8 molar than that of the iodide concentration for lead. Plus. Okay, so another funky part here is they can also do an like sample question here in terms of like, all right, well, what's going to be the copper concentration when the lead begins to precipitate? Because when you're adding it, the copper will continue to precipitate out, but remember, a small fraction of that is still soluble in solution. Okay, so but all this is this is just like a common ion problem. Okay, so we set it up the same way. So when the lead begins to precipitate, well, the concentration of I minus in solution is going to be equal to 0.0026 molar. Right? We figured that out already. So that's going to be our initial concentration for the iodide in solution. Okay? So our copper iodide little common ion problem here, plus an I minus. So it's 0.0026. This is 0 plus x minus x, or plus x. We get x and 0.0026 plus x. And then we're going to ignore that value, all right, to make it nice and easy. So KSP is equal to 5.3 times 10 to the minus 12, which is equal to the concentration of copper times 0.0026. So concentration of copper in solution at that moment is going to be 2.04 times 10 to the minus 9 molar. So there you go.